Good morning. Hope you're doing well today. I'm Ben. Today we're going to be talking about linear approximations, or also known as the Euler method. Euler method. So the big idea with this is you can take a derivative and turn it into a function. And that might not seem a big deal because derivatives kind of seem new and exciting and rare to you. But you find derivatives everywhere in life. Life is kind of run off of differences. You have difference of pressure, difference of temperatures, difference of potential energy, and that's what creates motion and movement and life as we know it. So oftentimes you're not really given the function, so to speak, in life, but you're given the differential equation, the derivative, the difference. And from that you have to then construct what life is. You already know all the basics for how to do this, and so I think the easiest way to kind of explain the concept is to just go through an example. So the example I'm going to use is, go to blue, y equals x squared. And you can also say f of x equals y squared. Same idea. And so one of the things we'll need to know then is the derivative. So f prime of x equals 2x. And we're going to take a point to start at. We'll say we're going to use the point 1, 1. And there we go, 1, 1. Point. And so normally, we said here that, okay, y equals x squared. Generally, that's not what we'd have to do the Euler method with. Normally what we'd have is someone would be like, well, here's f prime of x, or dy dx, equals 2x, and use point 1, 1. And even then, this is kind of easier than the normal equation we'd get to use Euler's method with. Euler's method is really meant for differential equations that are a little bit more complicated than this, and we can't, because for this we'd be like 2x, like, that looks a lot like the function x squared is f of x. So we just be like, okay, 2x. Later we'll learn integrals, but for here we'd be kind of guess and check x squared. We're like, oh, okay, x squared works, and we just draw the function x squared. Bam, super easy. That's not always possible. Sometimes you're given a derivative, a differential equation, and depending on how you look at it, most oftentimes in life, you can't actually take the integral. You have to just approximate it. And so it's very normal to be given a differential equation, and you can't get an explicit y equals or f of x equals out of it. And so you're left with just this in a dark, dark world, and you kind of have to make do, make the best you can. So the way we're going to do this is we're going to do it point by point. And so we know, just from life, I'm going to say her x is greater than 0. X squared will look kind of like something like this. And so what we're going to do is we're going to construct it point by point. And we're going to start at, I don't know, x equals 1 about here. And what we're going to do is we're going to use basically linear approximations, little teeny lines, to approximate y equals x squared. We're going to do it in a more formal, procedural type way, using a table. Everyone likes tables. So the way I'm going to set this up then is I'm going to say, I like purple. We have our x point, we have our y point, we have our dy dx, we have our delta x, and we have our delta y. Nope, terrible line. Actually, I could do a real line. There we go. Quite convenient. I'll do a few of those. Should I do verticals? I don't know. I'll just do horizontals. Horizontals are fine. Sufficient. So we're given our first point. We have 1, 1. We're given that here as our beginning. And we know our dy dx is 2x. So this is going to be 2x, which in this case will be 2 times 1. And then our delta x, our change in x, we've already said this time, every time we're going to steps that are size 1. So it'll be 1. And then delta y here is going to be dy dx times delta x. Another way of thinking of this would then just be dy delta x times delta x. Delta x is canceled, and you get something that's kind of sort of like delta y. as a general rule, when you see this d, that means its derivative, it's 100% accurate, it's infinitesimally perfect, pretty much. But when you see this delta as in a triangle, then you're going to think of it as imperfect approximation, which is basically what it is. We're doing a 1, this is going to be size 1 first step for dx. So for this then, we do our delta x times dy dx, so 2 times 1 will be 2. We use these to find our new points. So we know our first points were 1, 1. We knew the change in x is 1, so this will be then 1 plus 1, which is 2. The change in y is 2, so we do 1 plus 2, that gives us 3. Get some more. Oh, there we go. Do a few more just to feel safe and secure in life. Perfect. Go back to blue. Okay, so now we, again, our dy dx, derivative of y with respect to x, is still 2x. Because our initial function that we started with was x squared. Take the derivative of x squared, power rule gave us 2x. But in reality, for the problem, we'd probably be given 2x. So 2x, again, this now is going to be 2 times, but now we have 2. 2 times 2 is 4. And then 4, whoa, change in x is 1. This is 4. There we go. 1 times 4 is 4. So the y will now change by positive 4. So x increases by 1. Red. Y will then increase by 4. We give it 7. Okay, same thing. 2 times x. This then becomes 2 times 3, which gives us 6. X will increase by 1 because we're just saying it'll increase by 1 every time here. We don't have to say 1 every time, but it's usually easier if you do the same size step every time. And you generally get better accuracy, sometimes mostly, at least better consistency. It's also easier for computers if you program it. This works really well with computers because you can see we're just doing the same thing over and over again. Okay, so we do delta x times dy dx. 1 times 6 is 6. So 3 plus 1 is going to be 4. You know, I should change colors again just to keep it one color per row. Ooh, I really don't like this green. I'll give it a chance though. So 3 plus 1, 7 plus 6 is 13. One more row, 2 times x, therefore 2 times 4, which is 8, which at this point is probably not a surprise, equals 2. 1 times 8 is 8. And then we'll have our last 2 points that we have. 4 plus 1 is 5, orange. And 13 plus 8 is 21. So what we've done here is we've created a set of points, 2, 4, 5 points. We have 5 points that we then are using to approximate this curve y equals x squared. So I'm going to draw up a general idea of what we did here. So we have, let's do a line, line. Let's go with line. Line, click. There we go. Copy, paste. Go sideways. Come up here. There we go, that's pretty good. Maybe another one? Let's do another one. There we go. One side here. One side over here. And then we'll say, this is y equals x squared. Make curvy. Pow. And maybe like that. Okay. And so then what we did was we took this, started here. We'll say ended about there. And then we did a whole bunch. 1, 2, 3. Let's say like this. Like this. And then this one will be straight, but we'll make it a different color to add contrast. Blue. This one will be green. So I'll put some numbers on this just to kind of give an idea of where we're at. So let's say this is 1. Should get some better contrasting color. There we go. 2, 3, 4, 5. Maybe move this 4 over just a little bit. We can do better. Okay. Whoop. Blue. This one will be 4, 5, and let's say the last one is 6. Okay. So for us then, what we had was different color. We had the point 1, 1. That started off correct. And that one should probably actually overlap with the real one. It didn't. 2 goes to 3. 3 goes to 7. Looking over here. I did not have enough curve in this. 4 goes to 13. We'll say here. 13. And 5 goes to 21. At this point, I've realized my artistic skills are tragic. So, but then when we look at the points of y equals x squared, the actual graph, which is also not drawn to scale, y equals x squared, that'll be this guy up here, we have, well, that's okay, that's still at 1. It's supposed to be on the same, they're not. This is 4, 9, 16, and then 25. And so you can see that the approximation, they kind of sort of approximate, but they also are diverging by a little bit. First one's only off by 1, second one's off by 2, then it's off by, it looks like 3, and then 4. So they're all off, they're getting off by larger and larger amounts. So our approximation, those seems to be doing pretty well, depending on what your definition of well is. There's definitely a limit to how there's going to be some missing, some divergence. And that's the idea of the Euler method. So to recap what we did, because it felt like, oh, just, writing numbers up there, feeling crazy. Understand, I get the same feeling sometimes. We were provided with a derivative, a differential equation, f prime of x equals 2x. We made a table of points, like, all right, here's our first point. We draw, and what we did was we basically drew a line. I'm like, okay, here's this line, and then we took on there, I guess, line like that, and then we found the next point on the curve based on the tangent line. We then said, okay, that point that we approximated, we're going to assume that that's true, that that's the actual point there, and then we're going to use that point then as approximation for another one. So it makes sense if you have lots of little teeny errors along the way. Eventually, when you get really far out, you're going to have a massive number of errors until your approximation will get further and further away. And your approximation, so the way you make your approximation better, there's basically 2 ways. One is, if you want to approximate this point over here, you want a point really close to it to use as your starting base point. And the closer you start to with your, I guess, your base point, in this case our base point was 1, 1, and we built from there. That way you don't have to build as far, and that way your error will be smaller. The other way that you become more accurate is your delta x. So your delta x here is the step that you take. If you take a smaller and smaller step, you'll become more and more accurate. And so if you, instead of using a step of like 1, we use a step of like 1/10 or 100th or 1000th or 1/100000th, and then just took millions of steps, would be very, very accurate. Of course, then you have this trade-off of computational power versus how much accuracy you need. So a lot of times you don't need that much accuracy, and you kind of, we'll just do a couple big steps, wing it, close enough, oftentimes. Now the question at this point comes down to, all right, so now you kind of shown us this algorithm, this machine, this table that we can make and use. What do we do with this? Well, you can rote memorize it, just memorize it, burn it into your mind. This will be useful later in life, probably for most of you, at least a few times. But I think you're better off just kind of understanding the concept, knowing that, all right, if we start at this point, we can make a little line of a certain step and kind of work our way up. And I like to think, and it's usually best to think of it in terms of a graph. One of the challenge of challenges of thinking in terms of a graph is you really don't know what the graph is going to be until you start sketching it out. So usually when I kind of draw graphs, I kind of just, well, it's going to be something kind of like this. But the problem here is you don't even necessarily know if it's going to be up or down, and that can kind of throw you off. So I would not go with the rote memorization per se, because most of the problems you get for Euler's method on the AP exam will be relatively simple. And so if you can understand the concept of what you're doing, you can kind of just go through this and make it work. If anything, it might be worth memorizing that when you make the table, it's xy, dy dx, delta x, delta y. And having this table format kind of in your head to start with would be kind of useful. You should still do 4 or 5, Euler's method type approximation problems, but doing 4 or 5 is probably more reasonable than doing 40 or 50. Like, there are some things in calculus, like, the power rule, product rule, chain rule, where you should expect to do 40 or 50 problems using those properties. That way it's just burned into your soul of how to do them. It's very second nature. For Euler's method, it is important, but I wouldn't go to the same level of second nature that you would with a lot of other things. To take a step back, you might be like, well, this seems kind of, I understand it, I see where you're going with this, but it seems kind of tangential. Haha, it's a terrible joke, not intentional. I even wish I hadn't said it. But it feels kind of tangential, feels kind of unrelated, and it's not. It's totally related to what we've already done. If I write something up like f prime of x equals f of x plus delta x minus f of x all over, we'll do x plus h minus x, but then I'm going to, I shouldn't have written h, I meant delta x. But then when you simplify that, it comes out to delta x. You look at this and you're like, oh, well, yeah, that's the definition of a derivative. Well, if I rearrange this, move the delta x over and then move the f of x over, you have f of x plus delta x equals f of x plus f prime of x delta x. And if you look at what we did here, place this by, if you think of this, the f of x as y, then what you have here is the next value of y, this one, equals the previous value of y, that one, plus dy dx right here, times change in x right there. And so what we did was we just used the definition of a derivative, but in saying the limit as delta x, or h, goes to 0, we actually gave it a real value. In this case, we gave it 1. And so what we're doing is we're really just using the definition of a derivative over and over again to make this graph. And you're not really going to appreciate the value of what's going on here, because this is really big for computational analysis. Because a lot of times you are given a differential equation, or you create a differential equation to model a physical phenomenon, and you can then use that differential equation that you have to then create the model. And one of the things that becomes challenging then is you get different levels of stability or difficulty in modeling various physical phenomena. For instance, some things you can look at the derivative, map it out using an approximation. There are better approximations than this, but they're all basically the same idea. And you can get kind of a good idea of the graph. Well, when you go long term, or based on the differential equations, sometimes a very small error will create a huge error down the line. And you get what are called very chaotic functions. And they're very difficult to predict. And so there's a lot of real interesting implications with this whole concept here. Okay, sounds good? Let's do a quick example problem, something we might see from an AP exam. So let's say we have a problem here. Let y equals f of x be the solution to the differential equation dy dx equals x minus y. And this looks like the sort of thing that we would see with our implicit differentiation. And this is more like the sort of problem you'd actually encounter in real life, where you have both an x and a y as part of the dy dx. Later in life, we'll find out having both the x and y there makes it much more difficult to take the integral, and therefore using Euler's method to approximate this would be more reasonable. With initial condition f of 1 equals 3. What is the approximation for f of 2 obtained by using Euler's method with two steps of equal length starting at x equals 1? Okay, so first thought is, okay, Euler's method, let's write out our table, dy dx, delta x, delta y. Okay, so we got that down, and they gave us a starting point. Our starting point was 1, 3. X equals 1, y equals 3. So 1, 3. And we're also given dy dx, which is x minus y. So x is 1, y is 3. 1 minus 3 is negative 2. Change of x, so we're starting at 1, we're going to 2, and we're doing 2 steps. So 1.5, so we'll go from 1 to 1.5 to 2. That'll be 2 steps of equal length. To be more formal about it, you could be like, well, we end at 2, we start at 1, there's 2 steps, 2 minus 1 is 1, 1/2. Each step will be 1/2. So change in x will be 1/2, and we'll do 2 steps. Change in delta y, then you can think of, all right, dy dx times this, we have negative 1. Okay, so then we have x plus 1/2 is, I'm not sure if I want to do 1.5 or 3/2. I'm going to do 3/2. It's the same as 1.5. I get caught up on the minutia and the notation like that. It troubles me deeply. Okay, so now we want to find the change in y. Change in y is delta y, which is negative 1. So 3 plus negative 1 is 2. Okay, dy dx is x minus y. X is 3/2 minus 2 would be negative 1/2. Change in x is going to be the same every time. It's going to be 1/2. Change in y will be dy dx times dx, which is negative 1/2 times 1/2, which will be negative 1/4. So this would be like a non-calculator problem. And so non-calculator multiple choice, you have about 2 minutes to do it. At this point, I'm probably running over my time. You got to go through this pretty expeditiously. This is a lot of pencil work just to get one multiple choice problem done. But you'll see that some multiple choice problems are quick, some are longer. This is probably a longer multiple choice problem. Okay, focus. X 3/2 plus 1/2 equals 2. I'm just going to write that as 2. And then y would be 2 plus change in y. So there'd be 1 3/4, which would be the same as 7/4. And we were asked to find the approximation for f of 2 function when we plug in 2 for x. So the value then would be, this would be f of x, which would be 7/4. So, looking back, that would be the answer. So, the hardest part about this problem is getting your bearings, kind of figuring out where you're at, where you're starting from, what people want. Well, by people I mean the AP exam, what the AP exam wants to see here. And so, as soon as you read the phrase Euler's method, it should kick off, okay, I'm probably going to draw this table up. X, y, dy, dx, delta x, delta y. We're given initial points, 1 and 3, write them up. Dy, dx, you can solve for that. Then you solve for delta x, and delta x will pretty much probably be the same since they're all steps of equal length. And you'll usually see steps of equal length, but don't assume it always. It's a good trick. It's a trick question you might come across sometimes, that they're like, okay, these steps are all 1, but this step over here, that'll be 2. And then you'll do some more steps of 1. And like, it's a human performance trap, and you need to watch out for that. Then you solve for delta y each time and add that to the point, getting your new value. So this is how you do Euler's method and how you could expect to see this for the AP exam. So I hope this helped you understand a little bit about the Euler method. You won't come across a lot of questions like this on the AP exam. Maybe 3 to 5 questions that kind of deal with this sort of concept. Maybe fewer even. But it's really, really good to know. It's not that hard. And it is, as far as helping you understand calculus in general and how to use it in the future, it's pretty much essential. And this is kind of like the gateway into numerical approximations for things. So it's really good to know, at least in concept, the Euler's method. So I hope that helped. Next time we'll go over L'Hopital's rule, and that'll round out pretty much everything we didn't need to know about derivatives. After that, we'll do a review, and then it's on to integral calculus. I appreciate you stopping by. I will see you next time.